Assalamualaikum and hello to everyone. So in this video, I will be sharing with all of you the tutorial question, okay, for chapter 3, and this question will involve the isentropic efficiency for steady flow devices, okay, subtopic 3.9, okay. So we can read the question. So we have steam which enters an adiabatic turbine at 8 megapascal, 500 degrees Celsius, with a mass flow rate of 3 kilograms per second, and it leaves at 30 kilopascal. The isentropic efficiency of the turbine is 0.9, or in other words 90%. Neglecting the changes in kinetic and potential energies, we have to sketch the TS diagram and also determine number 1, the temperature at the turbine exit. Okay, the answer here is 69.09 degrees Celsius, and also the power output or work output of the turbine in units megawatt. The answer here is 3.05 megawatt. Okay, so before we begin, okay, just to highlight, since this question involves the isentropic efficiency, all the items which are asked in the questions, for example the temperature here, this one has to be the actual temperature. Okay, the actual temperature means T2A, okay, at the exit, and also this one has to be the work output actual. Okay, because why? Because we know the isentropic efficiency, that is 0.9 or 90%. Okay, so before we solve the question, let's list down the conditions first. So we have a turbine. So the conditions for turbine, the work input is 0. Adiabatic turbine, okay, Q in and also Q out is 0. Okay, and we can also neglect the changes in kinetic and also potential energies. Okay, so KE and PE are 0. So these are the conditions for the question. So then the question asks us to sketch, but for substance we know that the substance is steam right now. So for steam or refrigerant R134A, to sketch the TS diagram, we have to find the state first, okay, to confirm the phase of the state first, and then only we can sketch the TS diagram. Okay, so we can do that later. Okay, so let's proceed with step 1. So step 1 is to draw the schematic diagram for the turbine. So we have a turbine here. Okay, the shaft, the inlet is at the top and the exit at the bottom. So number 1 and number 2. Okay, so at number 1 we know the pressure is 8 megapascal. Okay, temperature is 500 degrees Celsius. Okay, at state 2 it exits at a pressure of 30 kilopascal. Okay, so the mass flow rate, okay, so the mass flow rate is 3 kilograms per second, and the mass flow rate at the state 2 is the same as the mass flow rate at the state 1. So this will produce a work output which we have to calculate. Okay, remember the actual work output. Okay, and the turbine has an isentropic efficiency of 0.9 or 90%. Okay, or 90%. Okay, so this is for step 1, which is to draw the schematic diagram. Now for step 2, okay, let's try to write the equation. So for the first item, the temperature, okay, the exit temperature, so that is the exit temperature. So Okay, so for exit temperature, so exit is at the state 2, so this is 2. And remember I said that since we know the isentropic efficiency, so the exit temperature here is the actual exit temperature. So this is a property at state 2. Okay, so later when we find the properties, we will try to find the actual exit temperature. And this is number 1. Number 2 is the actual work output. Okay. So we know the isentropic efficiency, so 0.9, and the isentropic efficiency is for turbine is the actual actual work output over the ideal work output. Okay, so to get the equation for work output, so to get the equation for work output, we have to write our SFEE. Okay, so we have our SFEE. So we write down our SFEE in capital letters because we know of the mass flow rate, and also the question asks us to find in capital letters. So we can write the SFEE in capital letters. Okay. So okay, once we have written down the general equation for the steady flow energy equation, we can cancel the terms based on the condition. So work in is cancelled, adiabatic turbine is cancelled, and the kinetic and also potential energy are cancelled. Okay, so from the general equation we can write down what is left. So on the left hand side we have the flow energy, on the right hand side we have the work and also the flow energy. Okay, so when we rearrange, okay, so we can get, so the work output is equals to the mass flow rate multiplied with the change in enthalpy. So this is the general equation. Okay, so general equation, okay, for work output. So we know now there is a isentropic efficiency, so we have to write this equation for the ideal and also actual conditions. Okay, so for ideal condition it will be work out ideal, okay, equals to m dot h2s h1 minus h2s. Okay, so this is for the ideal condition. For the actual condition, work out actual equals to m dot h1 minus h2a. Okay, so if we were to write it back in terms of isentropic efficiency, so we can get, okay, we can write it back. So isentropic efficiency equals to work out actual over work out ideal. So we can write it back. So m dot h1 minus h2a over m dot h1 minus h2s. So we can cancel the m dot. Okay, so we can get the isentropic efficiency equation. Okay, once we have calculated the once we have find the equation for actual and also ideal work output. Okay, so next so to find for work output, actual is actually, okay, m dot h1 minus h2a. So this is number 2. Okay, so next is the step 3. So we have to write the equation. We have to find the properties. Okay, so for state 1, we know the pressure is 8 megapascal or 8000 kilopascal. We know the temperature is 500 degrees Celsius. Okay, so as usual, table A5, 8000 kilopascal. We compare the temperature at state 1 with the saturation temperature. So we find that it's greater, so the phase is superheated. Okay, so superheated, we have to open table A6, 8 megapascal, and we look for 500 degrees Celsius. If we can read directly, we will read directly. If not, we have to interpolate. So I think we can read directly. So we will read for the enthalpy. Okay, 3399.5 kilojoules per kg. And also we will read for the entropy, specific entropy, because remember we have the isentropic efficiency. So we have to calculate for both actual and also ideal condition. Okay, so this specific entropy is for the ideal condition. Okay, so kilojoules per kg Kelvin. So this is for the ideal condition at state 4 later. Okay, so next we proceed with state 2. Okay, so state 2. Okay, so we know the pressure 30 kilopascal, and for ideal condition S2S here is equals to S1. Okay, so this is the ideal condition. Okay, this is ideal condition. Okay, so using table A5, okay, we have to check for the phase. Okay, 30 kilopascal. S2S we compare with SG. Okay, and I think so it's less, and when it's less we compare with SF. It's greater than SF, so the phase is mixture. Okay, so when we know that the phase is mixture, we have to find the quality. Okay, because why? Because to find for H2S, okay, is HF plus X HFG. Okay, so this one we can read from the table, 289.27, and this one we also can read from the table, 2335.3. Okay, so we don't have X, so we have to find for X first. Okay, so using the entropy, okay, we find for X. Okay, so rearranging the equation, okay, so substituting the values for SF, for S to S, 6 minus 0.9441 over 6.8234. Okay, so X we can get as 0.847. Okay, be careful with your decimal points. Okay, so I recommend 3 decimal points. Okay, do not try to simplify, okay, the decimal points. So if we can maintain it at 3 decimal points, we put it as 3 decimal points. So to calculate for H2S, okay, so 289.27 plus 0.847 multiply with 2335.3. So this will give us the ideal, okay, ideal specific enthalpy at state 2 as 2267.3, okay, kilojoules per kg. So this is the ideal. To find for the actual, okay, to find for the actual specific enthalpy, we have to relate it with the isentropic efficiency. So we know that the isentropic efficiency of the turbine is 0.9, and we have seen the equation just now that 0.9 is equals to H1 minus H2A over H1 minus H2S. Okay, so we can substitute the values, okay, to find for H2A. So H1 is 3399.5. H2A we want to calculate. Okay, 3399.5. H2S is 267.3. Okay, so when we calculate H2A, okay, when we calculate H2A here, we will get 2384.1. So this is the actual specific enthalpy. Okay, now for the question, it asks us to find the actual temperature. So now using this value, at state 2, okay, the pressure 30 kilopascal, we will compare H2A with Hg. Okay, so it's less than Hg, and then if we compare with Hf, it's greater than Hf. Okay, so we know that the phase is also still a mixture. Okay, so when the phase is still a mixture, we will read for the, so T2A here is equals to the T saturation. Okay, so that is why we get 69.09 degrees Celsius. Okay, so once we have all the phases, we can sketch the TS diagram. So the TS diagram, okay, TS diagram, it's a water, so we have the saturation line here. Okay, we have the low pressure, which is 30 kilopascal. We have the high pressure, okay, 8 megapascal. Okay, so we know state 1 is the superheated. Okay, for ideal conditions, straight line, so this is 2s. For actual condition, we make sure that it's the still mixture. Okay, so this is 2a. Alright, so this is the TS diagram. Okay, next is to calculate the actual. So step number 4. So substitute and solve for the work output actual. It's m dot H1 minus H2A. So 3399.5 minus 2384.1. So this will give us, if I'm not mistaken, okay, will gives us in units kilowatt. Okay, 3046.2 kilowatt. Okay, but the question asks us to find in megawatt, so we have to convert 3.05, okay, megawatt. Okay, so this is a tutorial, okay, for subtopic 3.9, isentropic efficiency for steady flow devices involving the steam turbine. Okay, so thank you.